Hello. Welcome to the session on hierarchical planning. And let me just mention that if you don't have an ICAPS tile, you can pick one up at the front. Okay, so in this session, for a change, we have 3 speakers. And the first speaker is Daniel Höller. Over to you.
Thank you for the introduction. So today I want to speak about some work on how to use classical heuristics in HTN planning. So in HTN planning, you have 2 ways to model details of a domain. You can do it via the preconditions and effects of actions, or you can do it via the hierarchy. I want to give a small example on that. So consider a small problem where a truck is located at position A and shall be go to position C, and we can model that by state, just introducing the current position of the truck in the state, and then we can introduce some action like at the right side where the position of the truck is changed via the effects, and then we just look for the goal at C. Now, the same thing can be modeled in HTN planning by the hierarchy. And this can be done by these 2 methods. So we have one method that decomposes an abstract task move into a direct drive action. And we have a second method that uses a recursion. And if we look at the method, we see that there is no actually position of the truck stored in the state during our search. But we know if we execute the task move AC that the truck will be at position C afterwards. So what we see at this small example is that though many people consider the hierarchy just as a way to introduce advice to the problem, we see that we can store just physics in there too. So it's just a way of modeling and not somehow bound to advice. Now we can, by using the hierarchy, represent quite complex problems. For example, the grammar intersection problem of context-free languages or post-correspondence problem that is actually included in our evaluation domains. And if we think about a planning problem, about all solutions to a planning problem as a formal language, we can express context-sensitive languages by using HTN planning, while we have regular languages when using scripts. Now, if we take the planner perspective, we might be provided with a problem definition that contains hard physics but no advice. So that's fine because the domain designer has less effort to model the domain and the problem, but for the planning system it's hard, and the system needs to guide the search. Now in the paper we propose progression-based heuristic search to solve such problems, and we make 2 contributions. The first one is an improved progression algorithm that I will not talk about here due to time. But we also introduce a method to use classical heuristics to guide the search, and I want to talk about this in the next slide. Now, if you use techniques from classical planning and HTN planning, you have a few problems to solve. The first one is the formalism is more expressive, and you cannot directly apply the same techniques as in classical planning. Think, for example, about delete relaxation. Delete relax HTN planning is even for quite simple HTNs NP complete, so we can't use that directly. On the other side, the hierarchy has a huge impact on the set of solutions. It determines which actions are actually reachable, and there is usually no state-based goal given, but the objective on what to do is somehow provided by the hierarchy. So our approach is we relax the HTN planning problem to a classical planning problem. This is a relaxation, so the set of solutions increases. Then we apply a classical heuristic to that problem, and then we use the heuristic values in our HTN planning system. So the actual search is done based on the original model, and the relaxed model is just used for heuristic computation. Before we go into details, I want to give a short introduction to HTN planning. So in HTN planning, there are two types of tasks. Primitive tasks that can be executed directly and cause state transition like actions in classical planning. And compound tasks cannot be applied directly. They need to be decomposed until all tasks are primitive. And we start with one or more tasks in the so-called initial task network. And now we decompose these tasks by using decomposition methods. So decomposition methods define how an abstract task is divided into other tasks. So for example, here in another abstract task, followed by a primitive task with an ordering relation in between. Here are two unordered abstract tasks, and the methods might even be empty. Now we are looking for decomposition of these overall tasks, and decomposition causes that the original abstract task, the decomposed abstract task, is removed from the network. The subtasks of the methods are introduced, and they inherit the ordering relations of the decomposed tasks. Now we do that until we found a task network with only primitive tasks, and then we need to find a linearization of these tasks that is executable in the initial state. So to sum up, in HTN planning, to have a solution, we need to have a refinement of this initial task network that contains only primitive tasks, and there must be the executable linearization of these tasks. Now let's come back to our approach. I want to show you the relaxation based on a small example. This is the example domain. You see here a simple delivery problem. So this is the overall task of the problem. So some package shall be delivered at some position, and this is done by getting to the package, pick it up, getting to the goal destination, and drop the package there. So the boxed tasks given here are actually primitive, and the non-boxed are compound, so they need to be decomposed. This is only the get-to task, obviously here, apart from the deliver task, and the get-to task has these two methods given below. So it can be decomposed directly in a drive action. It can be decomposed into using that recursive method. We have an intermediate position, and it can be decomposed to a no-op if we are already there. The blue labels given under the methods are just the names and the signature of the methods, so that we can refer to them on the next slides. Now, next question is, what do we want to compute actually? At the top here is a small transport problem given. So the truck is located at position A, package at location C, and as we can see at the topmost task here, we shall deliver the package at position D. And the tree that is given below shows how to decompose this initial deliver task. So you see the abstract task above, then the applied method, the subtask, and so on. And now, if we execute the box tasks at the bottom, we have our plan and can deliver the package. Now, what do we actually want to count is the number of modifications needed to find a plan. So we want to have the distance in our transition system. So we want to do satisficing search in the first step. So what we want to count is the number of method applications plus the number of actions. And so we end up with a heuristic value for the initial search node for that problem of 11 that we would like to calculate. Now, how do we do that? We introduce new state features, one for every task in the problem. And this somehow means that this task may be accomplished so far, may have been accomplished so far. So, for example here, there's this drive task and a corresponding state feature. And now, in the first step, we change the original methods in the domain by adding a new add effect so that they fulfill the corresponding state feature. So this drive action fulfills the corresponding task. And in the second step, we introduce new actions that simulate our method applications, but in a reverse order. So it's some kind of composition that is simulated here. You see that? So the method that decomposes the get to TB task into a drive TB is translated into an action with a precondition that is this state feature here, and an effect that represents this state feature here. So we somehow decompose our tasks. Another example here, the deliver the method that decomposes our deliver task. It will result in an action with 4 preconditions and just a single effect, deliver PD. And now, if we think about it, we can just search for a plan that fulfills the tasks in our current task network. So in this case, it's just the deliver task for the initial task network given here. And so what we have in that model is somehow the structure of the decompositions in a reverse order, and it's also informed about the state transitions. Now, the resulting model looks like that. As said before, it's just used for calculating the heuristic value, not for the actual search. And we see that it's composed out of the old actions with the added add effect and the new actions representing the methods. If you look at an application, the planner has to fulfill the tasks in a bottom-up order. So here we see one of the relaxations that's made. The get to TB tasks has to be fulfilled twice, and it's just fulfilled. It's the first time for both the actions, so for both the tasks. So we will get a lower heuristic value than is actually the perfect one. So we end up with a heuristic value of 10. We've seen why, because the get to TB task is must be achieved twice. So if you look at the heuristic, it simulates a task composition. While doing that, it incorporates hierarchical reachability information. It combines this information with state-based executability and also solves our problem of the missing state-based goal. Now, the transformation is actually a relaxation, so the set of solution increases, and it does so by doing the following relaxations. Every task has to be processed only once. We have seen that. The planner might, or the system that uses that model might insert tasks apart from the hierarchy, for example, to fulfill preconditions of other tasks, and the HTN ordering relations are completely ignored during heuristic calculation. Now, we show in the paper a way to reduce the task insertion, but it can't be prohibited fully. Now, the resulting model is quite large, but it's still linear in the input HTN domain. And there are a few parts that have to be updated during search. That's the initial state and the goal. So an efficient update is possible, but we need to use a heuristic from classical planning that can deal with changing goal states. A quite interesting property is that we can the perfect HTN solution in terms of modifications corresponds to a classical plan with equal costs, so we can construct safe and goal-aware heuristics, and with a simple trick, also admissible heuristics. Please have a look at the paper if you're interested in that. If we come at an empirical evaluation, we have combined our approach with 3 classical heuristics, the add, the FF, and the LM-cut heuristic. They all perform quite similar. But we can also see in the picture that even the algorithm improvements that we made brings some benefits. If we compare it to planners from related work, I've included just 3 here, as there are more on the paper. And what we see here is the number of solved problems over the time. It's a log scale, please be aware of that. And we see that we are quite fast and also solve the most problems with our new approach. To sum up, we introduced improved progression algorithm and proved that it's still sound and complete, like the original one. We introduced a way to use classical heuristics in HTN planning that incorporate hierarchical as well as state information, you can construct safe, goal-aware and admissible heuristics by using our approach, and the resulting system is quite compatible with the state of the art. So, thank you very much for your attention.
Thank you. And this won the award for Best Student Paper. An extra round of applause. Okay, questions? Okay, here we go.
Bad execution on my part. Hello, can you hear me?
Yes.
All right. So the example that you showed of computing the heuristic was on a completely developed plan decomposition tree. Mm-hmm. And it seems to me that the place where this approach could be especially useful is if you have a partially developed tree and you're trying to decide whether you want to extend it any farther or try some other tree instead. And I was wondering if you had thought about that at all.
So we use it in a heuristic search framework. So we have the initial task network given. We apply all modifications, and we sort the resulting search nodes in our fringe based on our heuristic. So I think we actually do that.
Okay.
So it was just an example and how to compute how the heuristic behaves.
Okay, thank you.
Thanks for the great talk. So one question I had is, here your objective function appears to be, your heuristics appears to be scoring the total number of method calls as well as the number of actions. But you can view these methods as simply artifacts in the problem solving process so that your final plan is hierarchically valid. And users might end up caring only about the total cost of the underlying plan. So is that as simple, if you want to address that, is that as simple as making the method action 0 cost, and then, would that still work?
Yes, so we wanted to construct satisfying planners in the first place. So that's why we estimate the goal distance and not the costs of the actions in the resulting plan. But we have already described that in the paper. You can just set the costs of the methods to 0, okay. And then you will have your cost measure that you would like to have. That's why the admissible is always has always been set in this parenthesis here. Mm-hmm.
Actually, I have another question. Okay. All right.
Okay.